gamma decays. What do I know about gamma decays? Gamma decays do not change the identity of a nuclei. They never change the identity. And so the way we can look at this thing here is that we could say the following thing here is that what they do is they do this here, is that the nuclei must start in an excited state first. So let me do this. The nuclei must somehow get excited first. That means here is that typically what this means here is that you need other decays to create an excited nuclei. So what this means here is that other decays, like alpha and both beta decays, to excite a nuclei, a unstable nuclei. And so what happens then is that we go from here, we take A. So then how do I write this? Okay, I'm trying to organize it. And so here's what you find here. So what you find here is that you find that this is the reaction equation. So the reaction equation goes like this. You start with a particle that's excited. So this is an excited, unstable nuclei. And how do we write an excited state? We put a star. So the star here means excited. And then what it does here, it goes gamma decay. Now, what do I mean by gamma decay? Well, what we find here is that it's going to fall. And as it falls, it's then going to emit light. And so in this case here, I'm then going to stay with exactly the same atomic mass and the same atomic number, and I still have the same particle. But now what it does is that it sends out a gamma particle. And so what you're seeing in this case is that I should have something like this, where this blue here means it's an excited nucleon or nucleus, right? It's an excited nucleus. So what you're seeing here is that the atomic mass does not change. And then it says that the atomic number does not change either. And so when we look at this thing here, what we're really having to do here is that we need some type of reaction that's going to make it, unstable. So here we go. So now to show you what I mean here is that let's look at this as an example here to show you what I mean. So molybdenum is a liquid radioisotope with a short lifetime. And these are used in medical imaging. So let's write this down so you can see what I'm talking about. So one example is that you have molybdenum. Oh, I forgot how to spell that. I should go get it. Here, let me go get it. So here we are. So I have molybdenum, and what it is here is that it's a radioactive liquid with a short lifetime. So it only lasts minutes. And what you find here is that these are used in medical imaging. So there's many different kinds of medical imaging, but this guy called SPECT is specifically, this whole goal here is that this guy here detects gamma rays. Okay, it detects gamma rays. So what's special about this? Well, what happens is that when you look at this guy, you go, this guy's 99, this guy's 42. I'm looking at one particular isotope. That's why I wrote this so you can see this. So this guy here is unstable. So now what happens here is that this goes beta decay. So what does beta decay do? Remember, beta decay changes the atomic number by 1. So now if it goes beta decay, look what happens. It's still 99, but then it converts 1 neutron into a proton. So I get the element 43, and that element becomes a technetium. And then during this process, there's a beta emission, right? So there's other things that's happening. So it's emitting that. But here's what's special about this. Technetium, it is now left in an excited state. So when I look at this thing, what I'm seeing here is that this guy is in an excited state.
I didn't understand that.
Gosh, you're seeing my watch going off here. So what you're finding here is that what I'm seeing here is that this is left in an excited state. And now we have a decay. And so what happens now is that this guy now goes gamma decay. And as this goes gamma decay, it then does not change its numbers, right? It does not change its numbers. And it goes like this, and then it emits the gamma. So the question is, what does this picture look like? So if I look at this picture here, this is what I'm seeing. I'm seeing that molybdenum, ooh, that's not the way you pronounce it. It starts right here. And this guy is now going to beta decay. So it goes this way, and as it goes this way, this becomes, it emits a beta minus particle. So what it does here is it now leaves this titanium in an excited state. Okay, so this guy now is in an excited state. So in this process here, this is a higher energy state. This guy is a lower energy state. So what does it do? It falls. And as it falls, I now have de-excited titanium. And then what does it do? It emits this very, very high energy gamma. Right? It emits this very, very high energy gamma. And so it is these gamma rays, these gammas are detected by the apparatus SPECT. And these are images that they can produce. So when you look at the medical imaging of this thing, you're seeing this guy here. So this is the actual image right here. And what they do here is that they come in here and then they do this. Then they do what's called a false color image. And then what it does here, you could go in and you could then look at it. So these guys are false color images, and they give you the details of what is going up. So in essence, what these gamma rays are doing is that they're lighting up the brain so you can look at what's happening in part of the brain. I remember many years ago, before my father passed, he had to take a radioactive liquid, and he had cancer of the esophagus, and they were watching on an x-ray machine as this, I don't know, it wasn't an x-ray, I believe it was a SPECT, and you could actually see the radioisotope. They had a movie of it as it would go, live movie, by the way. They were looking right at his esophagus, and it was lighting up the esophagus because it was emitting gamma rays.